Okay, so we are going to just kind of review a little bit about what went over last week. And this is actually what we did in lab today even. So why are specific substances water soluble, water insoluble? So it's really all about, the bottom line here is similar, and I use that word very loosely, but similar intermolecular forces. Ions in a solid are held together with fairly strong ionic bonds. If those ions are going to be separated, to dissolve them in a liquid, you need a liquid that is going to have fairly strong IMFs. And that's water. Water has hydrogen bonding, one of the strongest types of IMFs. And so, salts will dissolve in water. Not all salts. If your salt has +2, -2 charges, MgO, magnesium oxide, maybe that ionic bond is too strong for water to interact with, and so that's insoluble. So the forces involved between the two substances have to be not the same, but they have to be similar, on the same level. So when you get down to organic stuff, like this is ethylene glycol, the antifreeze, it does hydrogen bonding just like water does, so those will mix very, very easily. This is an alkane, which only does dispersion forces. And this is how it would interact with water if it does. And, it's possible to have very, very rare occurrences where water interacts with this alkane. What is it? 1, 2, 3, 4. It's octane. Just, the stuff in gasoline. When you need to buy the more fancy, higher priced gasoline, you have a little bit more of the octane in it. But the thing is, water's interaction with itself is much, much stronger than water's interaction with alkanes like this. And so they're not going to mix. These alkanes are not going to be able to interact with water very easily. Water would rather interact with itself. And so they're going to stay separated. This alkane will interact with other alkanes fairly easily because they are going to have the similar intermolecular forces. All right, so like dissolves like. We're being a little bit more specific. So in this case, which of these is insoluble in water? You need to be able to tell not just from the picture, but from the names. This is coming into understanding what these functional groups are. Which one of these is insoluble in water?
Which slides do you have open right now?
This is deck 10, I think. Slides at 10?
It's 10.
Yeah.
Okay, thank you.
Okay. So most people got it right. It is the only one that's really insoluble is pentane, because the A-N-E ending indicates an alkane, and these are just hydrocarbons with single bonds between the carbons. That's it. There's no other functional group. So these are going to be pretty non-polar molecules. They're only going to do dispersion forces. The pentanol, the two-part, don't worry about it, but the OL ending, that indicates an alcohol, that OH group. And as soon as you see an OH group somewhere in the molecule, you can say, oh, that does hydrogen bonding. That OH bond, covalent bond, is very, very polar, super polar. And it does strong hydrogen bonding with other molecules that have dipole moments in them. So that's going to dissolve in water pretty well. It's like ethanol. Ethanol and water mixed together. This is just a slightly longer chain. At some point, I'll just say this, at some point, you could have a really long carbon chain with an OH on it. And the long part of the carbon chain might make it insoluble in water, no matter what kind of thing is on the end of the group. It really depends. There's a balance. We're not going to give you examples. I'm not going to try to trick you on tests with those kind of examples. But you get gray areas at some point, and we saw that in the lab today. So there you go. Alkane, pentane, when water, they would not mix. And we'd say that's immiscible. That's the word you'd use. So I don't think we saw this specifically, but we did talk about how a DNA double helix, it's this backbone is made of a sugar and a phosphate, sugar-phosphate, so it's just a long chain of these repeating units. And then attached to the sugar part is a base pair that looks like one of these four here. And that's it. That's what DNA strands, the helix is made of. The double helix, the fact that two of these are wrapped together and they're connected, they're not connected by any bonds. They're connected by intermolecular forces, these hydrogen bonds. And these are the four base pairs, adenine, thymine, guanine, cytosine. If you remember the mnemonic, Alice talked to the grinning cat, that's how you know which goes which. So this links with this, and that's it. And that's because these are perfectly shaped to do these interactions using via hydrogen bonding with the other base pair. Guanine and cytosine go together because they are shaped to do this kind of interaction. So this will not work with that. That will not work with itself. For instance, you have to match the right base pairs. So DNA is held together using just plain old hydrogen bonding. And that's how it unzips. It has to, I don't know the ins and outs of it, but RNA transcription, so RNA comes in and copies the DNA code, it has to unzip somehow. So these are not covalent bonds that hold it together, just regular IMFs. Okay, so we're going to switch gears a little bit. We've talked about some properties of substances that you can kind of predict now via intermolecular forces, so surface tension and viscosity and capillary action. So another one, and we're going to use the same picture from surface tension to kind of explain it, is something called vapor pressure. So vapor pressure is a property we can measure from any liquid. And what it does is it dictates how much vapor is generated from these liquids. So when you think about water evaporating, water evaporates because this liquid, even though it's not at the boiling point, will generate vapor, gas particles of water that just kind of leave. And eventually the liquid water will be gone, and all of it will turn into a gas. So how does this work with IMFs? Well, again, IMFs are what holds molecules together in a liquid form. You have to break those intermolecular forces for a liquid particle to turn into a gas. And if you think about it, well, a particle at the surface of a liquid is probably a little bit less tightly held on than something on the inside. And so these surface particles, if somehow they were to get the right amount of energy, then that energy could be used to break the neighboring attractions, and now it could fly off as a gas. Okay? So that's the kind of thing you have to think about. And when you consider a whole bunch of molecules in a container, they all have kinetic energy. They're all moving around. That's what makes them a liquid. Even in solid, they vibrate, they move. But in a liquid, they're definitely moving around. And they all move around at different speeds. They all have different kinetic energies. It's like if you're playing the game pool, and you got your white ball, and you hit it, and you break all of the balls, and they all start moving, some going fast, some going slow. They bounce off each other. One that's moving will suddenly go slowly or stop, while the other one that was stopped is now moving. That's what's happening in this chaotic situation. These are all colliding, they're moving around, they're transferring energy. They all have slightly different energies. And those collisions, sometimes you'll get a case where, hey, I hit this molecule really hard, now this molecule has a ton of kinetic energy, and it's already at the surface, and it's got enough energy and it's going to leave. So some of these molecules have the right amount of energy to break those attractions with their neighbors. Some of them don't. And even if they have the right amount of energy, if they're not at the surface, they could just collide with something else, transfer some of their energy somewhere else, and then suddenly not have the right amount of energy. So it's like a shifting scenario all the time. But again, some of these molecules do have the right amount of energy, and if they have the right amount of energy and they're at the surface, they will vaporize. They will evaporate, turn into a gas. So this is where we have to dip our toes into something called the kinetic molecular theory. And this is just a model of trying to understand how molecules behave. And in kinetic molecular theory, we basically say that the average kinetic energy of a group of molecules, so average, when you average them all together, is directly proportional to the temperature of that liquid. All right, so the hotter the liquid is, the higher the average kinetic energy. And so that's kind of what we're trying to show here. These trails kind of dictate, oh, and by the way, kinetic energy is also proportional to the velocity squared. So the larger the kinetic energy, the higher the kinetic energy, the faster these things are moving. Okay? So anything with a long trail means it's kind of moving fast. Anything with a short trail means it's moving slow. But on average, it's got a certain amount of kinetic energy. And so you can see the low temperature, on average, they're slower. On higher temperature, on average, they're faster. That's basically what we're going to get from the kinetic molecular theory. We're going to devote more time to this when we get to the gas chapter. But that's what we'll do for now. And let's kind of mathematically look at what, how, so instead of looking at an average, let's look at the actual kinetic energies for all of the molecules in a collection, as a collection. And we've seen this curve before. This is called a Boltzmann distribution, or a Maxwell's-Boltzmann distribution. There's longer versions of the name. And all this is showing is, on the x-axis, the kinetic energy. So we go from 0 or low to high. And the y-axis is number of particles. And some people had, in my last class, had a hard time visualizing what does that really mean? And so what I like to think of is, well, if I've got a container and I think of them as proportions, think of like way higher up is 100% of all the particles, and like this is like 10% up here. So you've got a small fraction going this, a smaller percentage going like this, a smaller percentage here. Maybe 10% of the particles are going this kinetic energy. So if you break this into like slices, that's kind of another way to think of it. Basically, one of these curves, let's focus on the lighter one, the T1. If you, calculus-wise, don't worry if you haven't taken calculus, but calculus-wise, the area under the curve represents all of the molecules in your container. And so if you think of these in little slices, take a little slice here, you've got a certain number of molecules that have very low energy. You've got more molecules at a slightly higher energy. You've got even more molecules at an even higher energy. And as you go to higher and higher energies, you get to this peak where you've got a lot of molecules at this peak energy. And then as you go higher and higher energy, now the molecules, you start to get fewer and fewer molecules. So even over here, at the super high energy, you've got a small amount, but a measurable number of molecules have this energy. Out of the whole container, only a small fraction of them have it, but that's what this is saying. So that's what this Boltzmann distribution does. It kind of just shows you a representation of the energies of all of the molecules. And this temperature, so based on, so here T1 is a low temperature, T2 is a high temperature. This is showing what happens to this Boltzmann distribution as you increase the temperature. So number one, this peak here shifts to the right, and then at the same time, this curve broadens out. So as you get to higher and higher temperatures, the peak shifts to the right. You get to a higher kinetic energy for that peak, but it also spreads out the distribution of energy. So you get a bigger distribution of energies. It's not all concentrated into one little small amount of energy. You get a larger number of energies. Okay, let me see if this works. I forgot this one. No, this one's not going to work. Yeah, that's what I thought. Okay. So let's make sure that this distribution thing as a whole makes sense to us. And so if I were to ask you what is the most probable kinetic energy in this Boltzmann distribution, which line would represent the energy? This energy here, this energy here, this energy here. Which line represents the most probable energy? I think we've talked about this, so it should be not too bad. All right. So I know people are confusing probable with the next thing, which we'll talk about in a second. But the most probable is going to be where the maximum peak is. The idea is I take a random molecule out of my container. What is the most likely kinetic energy for that molecule? Well, it's not always going to be this energy, but the most likely one is the one where I have the most molecules having that energy, and that's it. So I have the best chance of getting a molecule with exactly this energy. Of course, I could randomly pick one of these too, but I have the most molecules at that energy, so I'm most likely going to pick one of those. Now the next thing is which kinetic energy represents the which energy represents the average kinetic energy of this distribution of energies. So average, I take every single molecule, I add up each one of their energies, I divide by the number of molecules I have, and I will get a number. And yeah, you get it right, okay. And that number is going to be C. So exactly where it is, this is kind of roughly put, but the average is going to be somewhere to the right of this peak, and that's because, again, this peak is not symmetric. It's not a perfect parabola. It's not even a parabola, but it's not even a perfect, it's not symmetric. On this side, the curve just tapers off. It kind of doesn't just go to the zero. It kind of just tapers off on this side. So the average is actually pulled over here somewhere. Okay, and that's that average that we can correlate to the temperature. Yeah.
Is there like a maximum kinetic energy that a particle could have? I suppose like the speed of light, right, or something like that.
Yeah, I guess it would be the speed of light. I mean, things start getting weird when you approach the speed of light, but yeah, so yeah. I don't know if that equation still works. The 1/2 mv squared still works when you get closer to the speed of light, but for classical mechanics, that works, yeah.
Okay, fair enough.
Yep. So this is an interesting question, and if you have taken calculus, hopefully this makes a lot of sense to you. If you haven't, it should still be okay. If I am talking about, well, which region of this graph, so I'm talking about molecules that are represented by this graph, which molecules would have enough kinetic energy to escape the surface of a liquid? And so which shaded region represents these certain molecules that do have the right amount of energy to escape from the surface of a liquid? I did turn it on, right? Yeah, okay. So we've got a couple people voting B, most people voting C. It's totally understandable why you might vote for B, okay? Because you think, oh, tallest, highest peak. But remember, the y-axis represents the number of particles, and the x-axis represents energy. Kinetic energy. So we want a molecule with a large amount of kinetic energy. That's going to be the one that's going to be able to break free from the neighboring intermolecular forces with its neighbors. So only molecules that have a high amount of energy. So while molecules in this area may have the right amount of energy, it really depends on what kind of intermolecular forces we're dealing with here. Definitely something with higher kinetic energy will be able to escape too. So it's pretty much, there's going to be some threshold, whether it's here, or here, or here, but anything beyond that threshold, so here it's here, anything beyond that threshold, anything higher energy than that, here's the minimum energy I need to break my intermolecular forces. That's my minimum energy. In this particular case, anything higher than that will be able to escape. All right, so the molecules represented by this area under the graph here all have the right amount of energy, or more than the right amount of energy to escape. Okay?
You said they're higher than the threshold?
Right, so there is some, so when you have two molecules that are interacting with each other through intermolecular forces, they have lowered their overall energy. And you have to add energy to break those attractions. So whatever that energy is required, that's the minimum energy you need. That's that threshold. So wherever it is it here, is it here? It really is going to depend on what molecules we're looking at. So if it's a molecule with really strong IMFs, that energy you need is going to be pretty high up. If it's really weak IMFs, maybe it's a lot lower. Okay? So here is we're not going to do this lab, I realized, but one of the consequences of understanding evaporation is, and how it works and what happens, is something called evaporative cooling. And that is that as things evaporate, they tend to cool down what remains. And so if these molecules are left behind, because they don't have enough energy, these molecules have enough energy to leave. Let's say they do leave. They left the liquid, and now they're gas. Well, the energy that they had that contributed to the average kinetic energy, well, they took that energy with them. So now that energy's gone, what is the average kinetic energy going to be now? It's going to be lower than what it was. And average kinetic energy is proportional to temperature. So if the average kinetic energy has gone down, the temperature is going to go down. Yeah, so everybody got that. The temperature is going to go down. Let me go back one point, Chase. So this is how sweating works, really. You sweat. You generate liquid that comes out of your pores, and the sweat will eventually evaporate. So some of those sweat molecules have enough kinetic energy to evaporate, and when they do, they take that energy with them, and the remaining energy now is on average lower, and so your temperature is going to be lower. And that's why we sweat, so to lower our body temperature. If you've ever, you can feel water evaporating off your fingers. You can feel it get cool when it does that. But if you've ever gotten acetone on your fingers, that gets a lot cooler. You can really feel it getting cold when it evaporates. And that's because the intermolecular forces of acetone are weaker than water. And so that threshold for, what energy do I need to evaporate? I don't need as much anymore. So if it's a smaller amount of energy, guess what? There's a lot more molecules that can evaporate more quickly. And so those are going to evaporate. It's going to cool down a lot faster. So evaporative cooling is a neat little concept. Okay. So here, we're still talking about evaporative cooling. I've got these two graphs. Only one of them is right. And I have this minimum energy needed for liquid A or liquid B to, once this molecule has enough energy, it can evaporate. So which one is correct, given that I'm telling you liquid A has stronger intermolecular forces than liquid B?
So how does a heat lamp work? If it's because you're having transmission of heat through air, does that mean that it's heating up the air, the gas around it? It's transmitting. It's infrared light. Yeah.
And yeah, it's going to be heating up the air, but yeah, some of it reaches your skin as well from just infrared light.
Why can we feel infrared as heat though? That's a way.
Because it is very low energy. And okay, so when we talked about promoting electrons from low energy levels to high energy levels, we really were focusing on atoms at the time in 221. And so all atoms have are those energy levels, and that's it. Whether they have the subshells too, but that's it, just energy levels. But when you talk about molecules, in addition to the energy levels that you get from the MO diagrams, we also have bond vibrations. And so we have only focused on electron energy levels. In addition to electron energy levels, there are things called vibrational energy levels. So even the bond vibration is quantized, and you can have different quantized vibrations. We kind of briefly looked at that with the greenhouse gas lab at the end. But in addition to vibrational energy levels, there's also even smaller rotational energy levels, so molecules spinning. So anyway, going back to the vibrational energy levels, the energy required to go to different vibrational modes is a lot smaller. So infrared is readily absorbed by everything that is molecular. So yeah, it's a small energy. It's high wavelength. Yeah.
Okay, cool.
Anyway, that's a different class because you'll talk about that vibrational energy levels if you take quantum mechanics as a chemist or a physicist.
That's next semester, right?
Third year. All right, so this question, this is really just about understanding this graph. And I think for the most part you guys do. So again, stronger IMFs mean you need a lot more energy for those molecules to break the IMFs and actually be able to escape as a gas. So the threshold energy for something with strong IMFs is going to be a lot higher, and only a small number of molecules are going to have the right amount of energy to escape. Whereas if you've got weak IMFs, that threshold energy is going to be lower, and there's a lot more molecules at a given temperature that can escape that liquid. Okay? So that is the correct graph for something where A has a stronger IMF than B does. So as a follow-along, which one of these would do better evaporative cooling? All right. So most of you got it. It is B. Okay, so again, evaporative cooling works best when you have lots of molecules ready to evaporate at a moment's notice. And for A, only these molecules are ready to evaporate. For B, all of these molecules are ready to evaporate. There's many more molecules that can evaporate, so B will cool down a lot more from evaporative cooling than A will. So we looked at IMFs, but IMFs are not the only indicator of how well something can evaporate. What about temperature? So if you look at these two graphs here, these are two different Boltzmann distributions. These are two different temperatures. Like I was saying, as you increase the temperature, the average kinetic energy goes up. So here, this is the most probable. The average is right about here somewhere. On this graph, here is the most probable. Here's about the average here. So the average has gone up. And, so again, on the x-axis, and the peak is, or the curve is more broadened. Now I want to warn you that we're not looking at the same exact Boltzmann distribution as before. Notice on the x-axis we have speed now. And while they may look similar, the kind of assumptions we make are a little different. So kinetic energy is proportional to the temperature. The average kinetic energy is proportional to the temperature. So in this equation, well, it's not an equation, in this proportionality, only temperature matters. That's the only thing that's going to affect the average kinetic energy, that distribution of speeds. But if you now compare not with the kinetic energy, but let's convert this kinetic energy to the speed equation. It's a lot more complicated when you're looking at how does velocity change. Because in addition to velocity being affected by temperature, mass is going to affect it too. So be careful when you're comparing different molecules that have different masses, and whether you have on this x-axis, is it kinetic energy or is it speed? If it's speed, it's not just the temperature that's going to affect things, it's going to be their masses too. We'll talk about that later, but I just want to point that out, that Boltzmann distributions, you can have two different x-axes, or at least the ones we're going to look at, you're going to have two different x-axes, and you have to pay attention to which one it is. Anyway, coming back to these two. We can relate speed to kinetic energy, that's what we're going to do. We can still draw that threshold. What's the minimum energy needed for this particular molecule to be able to break its IMFs and go from a liquid to a gas? And these two curves are for the same molecule. All they are is different temperatures. So that threshold is going to be the same for both of them. And you can see that for the low temperature one, the blue one, the area under the curve is only so big. But if I look at the orange one, the area under the curve is much bigger. It's the whole space, including this part here. And so the idea here is the higher the temperature, the more evaporation is going to take place, because I have more molecules that are at the right kinetic energy to evaporate. And that should make sense to you, because if you take room temperature water, it will evaporate, but it takes time. If I've got water heated to like 70 degrees and I just leave it at 70 degrees, it will evaporate a lot more quickly, okay? And that's because you've got a higher proportion of molecules that are at that right, over that threshold energy that can break the IMFs. Okay. And there's the same thing. So here we've got kinetic energy again back on the x-axis, not just velocity, but same idea, same as before, same as the last slide. Now, let's talk about vapor pressure and what that is. Because I mentioned that before. That's the property that we can measure that is correlated to IMF. So let's first talk about, what happens in evaporation. So we've been using all these examples where I leave a puddle of water out or leave acetone out. It evaporates, it disappears. That's what happens. So that's if you have an open container. If I've got an open container of a liquid, over a certain amount of time, that liquid will just turn into gas and evaporate. But what if I have a closed container? Does evaporation still happen? The answer is yes, it does. But when these liquid particles turn into a gas, they're trapped in this space. And sometimes, and it's not static, meaning once they turn into a gas, doesn't mean they'll stay as a gas. They're bouncing around. Gas particles are flying around, bouncing around, and they might strike the surface of the liquid again. They will eventually. And when they hit the surface of the liquid, what happens? Well, they get reabsorbed. It's like the billiard ball game, pool. They'll hit the surface of the liquid, transfer some of that kinetic energy to the liquid, and they'll have not enough energy to bounce back out. They'll stay stuck. But while a gas particle is turning back into a liquid, well, there's going to be other liquid particles ready to turn into a gas. And there's going to be this back and forth where liquid turns into gas turns back into liquid. This is what we call an equilibrium. Okay? And so when this equilibrium has been reached, where you've got your liquid particles turning to gas particles turning into liquid, and they're going at the same speed, like the amount of gas is effectively unchanging, where it looks like there's the same amount every time. We can measure the pressure of that gas. And we're not going to talk about pressure yet, but exactly what it is. But pressure is a way of measuring a gas, how much of a gas there is. And we can measure that pressure. We can basically measure exactly how much gas we have. And that's what we call a vapor pressure. So we're measuring the amount of vapor that is being generated in a closed container. Because if we have it open, then it just keeps escaping, and there's nothing to measure. So this curve here is just kind of showing you mathematically what's happening. So I take a liquid and I put it into a container that has a vacuum in it, nothing. So I take a container with nothing in it, no air, and I put a liquid in, and immediately at time 0, what'll happen is that liquid will start to evaporate. And the rate of evaporation is constant, meaning there's going to be a steady stream of liquid particles turning into gas particles. But as I start generating gas, that's what's happening here. I start generating gas particles. Some of those gas particles now are going to go back into liquid. And that's what this is, the rate of condensation, the gas turning back into liquid. So it starts off at 0 because there's no gas particles. And as I make gas particles, some of those gas particles are going to turn back into a liquid. And the rate of condensation is going up as there is more and more gas particles available. When the rate of condensation and the rate of evaporation reach the same speed, they're going, hey, I'm making 10 per second in both directions, whatever the number is. That's not the number, but whatever the number is, that's when we say we've reached equilibrium. And that's when we can measure, hey, how much gas do I have? And that the amount of gas that I have is going to stay constant. The particles won't stay constant. There's going to be constantly going in and out, liquid to gas, gas to liquid, but the amount of gas that I have is going to be constant. And that's our equilibrium vapor pressure. FYI, the way we measure pressure, and this is the old school way, we use an instrument called a manometer. It's a U glass-shaped tube, or glass U-shaped tube, excuse me. If it's not connected to anything, the level of mercury inside, that's what's inside, is mercury, will be even. The two sides will be completely even. These will be level from gravity. But if I connect it to a container that has a higher pressure, and you guys, I think you understand intrinsically what pressure is, more force, air is more forceful than the atmosphere on the outside, then that pressure is going to push on this mercury. This is going to go down, this is going to go up. And the difference in the height between these two mercury columns is the pressure. And so we get weird units like millimeters of mercury. That's a unit of pressure. The weather report on TV uses another one, inches of mercury. That's a pressure unit. And it comes from this old school device called the manometer. Okay, we don't use it anymore because it's full of mercury and it's dangerous. But that's where our pressure units come from, or at least some of them. Here's another view of a dynamic equilibrium that occurs. So we start with just pure liquid, nothing else, no gas, a vacuum. And suddenly the liquid starts making vapor. And some of that gas, that vapor, will turn back into a liquid until you get the same rate going back and forth. And it's called dynamic because even though the amounts are not changing, it's dynamic in the sense that the molecules are constantly recycling, going up and down, turning liquid to gas, gas to liquid. Okay?
It's like a terrarium.
Yeah, exactly, yeah. But occurring at much higher speeds. Yeah. So this is another kind of manometer. The other one was open. It was open to the atmosphere. This is a closed manometer. There is a vacuum here. So this one, you hook up a liquid that you just put into a flask that had a vacuum in it. So there's no gas. So the level of the manometer is even. Vacuum here, vacuum here. But over time, that liquid will create vapor gas that will have a pressure, and that pressure will push the mercury downwards, and then you can measure the vapor pressure. Okay? So the more gas it makes, the lower that threshold for that, how much energy do I need to break my IMFs. So the weaker your IMFs, the more gas you're going to generate. And the more gas you're going to generate, the larger your vapor pressure. All right, so the higher the vapor pressure, the more gas you're going to be making, the more evaporation that's going to occur. Okay, so here's another graph. Let's see if we can understand what we're seeing. This graph shows temperature on the x-axis. And on the y-axis, we have vapor pressure. So again, the higher the vapor pressure, the more evaporation that's occurring. So which one of these, if one of these is water and one of these is ethanol, which one of these is ethanol? See if you can puzzle it out. Okay. Everybody's got an opinion. Good. So, there we go. Oh, good. Everybody thinks it's A. Most people do, I should say. And it is A. So, the easiest way to kind of read one of these is pick a temperature. You know, I don't know what it is, but like, let's say it's here. Let's call this room temperature. If I'm at room temperature, one of my gases has a fairly low vapor pressure. Or I shouldn't say gases. One of my substances has a low vapor pressure. And at the same temperature, the other one has a higher vapor pressure. There's more evaporation. Well, which one would I expect to have more evaporation? The ethanol, because it has weaker IMFs than water does. So something that has weaker IMFs should evaporate more. And so that makes sense that A is describing the ethanol one. Now, the other thing that this curve does is it shows you that as you increase the temperature, the vapor pressure goes up. Well, that makes sense because we just saw those Boltzmann distributions. As you increase the temperature, the peak of the Boltzmann distribution shifts to the right. The curve flattens out a little bit, and you have more molecules past that threshold, so more evaporation is occurring. So this makes sense. This fits with that. Here, let's see what this is. Oh, yeah, I like these. Oh, commercial, sorry.
Jess wanted to start a business when something surprising happens.
Today, I'm going to teach.
So these things, how do they work? Hold in your hand, liquid drains out of the bottom bulb, goes up. So, can't see the construction super well, but I'm going to point to one of these. The way these are constructed is you've got this bulb on the bottom, and there's this glass straw that is not all the way touching, but it's really close to the bottom of this flask. And this is sealed, but the glass straw goes up into this bulb on the top. So when you hold, and the liquid inside is something that has fairly weak IMFs. It's just colored as well, but it's fairly weak IMFs. So when you hold this flask in your hand, the heat from your hand, it heats up the liquid. And what happens when you heat the liquid? What happens to the distribution of molecules of kinetic energy? It flattens out. You're going to have more molecules that have the right energy to turn into a gas. So more evaporation is going to occur, basically. So as you're holding this in the palm of your hand, more evaporation occurs. So this liquid makes more gas. Where does the gas go? It's a sealed container, so the gas goes in here. But you can't have an infinite amount of gas in this space. This gas is taking up space. And so how is it going to have room? Well, it's going to push the liquid out of the way. And the only place the liquid has to go is up the straw. So you're generating gas in this open space here. The gas is pushing the liquid out of the way, and it's pushing the liquid up to these bulbs up here. Yeah?
Is this how like the drinking birds kind of work?
I actually don't know. I don't know how they're constructed, actually. It might be. I don't know. I'd have to look it up. I actually don't know. Yeah, they go down and they go up, and then go down. Yeah. I don't know. But these are fun. Okay. So here is another with data with actual numbers on it. Vapor pressure diagram. And this one has 3 different substances: water, ethanol, and diethyl ether. And there's a lot you can get from this. You can look at the water one. You can say, well, at room temperature or so, it's around here. The vapor pressure is really low. It's like barely readable. So that tells you that even at room temperature, water is going to take a long time to evaporate. But if I heat the water up to around 80 degrees, that vapor pressure is already really high. It's making a lot of vapor. And so it should evaporate pretty quickly. How much vapor is it making? The pressure is around 350 millimeters of mercury. These units might not make a lot of sense to you, but just remember that the higher the vapor pressure, the more evaporation that's occurring. Now, there's more that we can get from this. And so we know the boiling point of water. We know the boiling point of water is 100 degrees C. So if you look on this curve and look at, okay, 100 degrees C, the vapor pressure at 100 degrees C is 760 millimeters of mercury. That's actually a special number because that is standard atmospheric pressure. So if you're at sea level, not on a mountain or anything, and it's a normal, perfect weather day, the atmospheric pressure should be approximately 760 millimeters of mercury. So that's a special number, and there's a reason the boiling point is where it is. And that is because when any liquid, its vapor pressure reaches the same pressure as the atmospheric pressure, that's when it'll boil. So if I look at diethyl ether, and I say, oh, okay, when does its vapor pressure equal the atmospheric pressure? It equals it at about 34.6 degrees C. That's its boiling point. So you can get boiling points from these diagrams. Not only that, what if you were living on a mountain? So if you're in Denver, the Mile High City, you're living a mile, over 5,000 feet high in the sky. And we'll talk about this in more detail, but the closer you are to space, the less air is on top of you. And the less air that's on top of you, the less pressure, the less atmospheric pressure you're experiencing. So, in Denver, they experience a lower atmospheric pressure. It's not 760 millimeters of mercury. It's going to be, let me think what it would be. It's going to be 600 something-ish millimeters of mercury. So what that means is if the atmospheric pressure in Denver is normally 6 something, around here, then that would mean that water would boil at around 95 degrees C in Denver.
That's why your microwaves have a setting on them that changes how they function or how they heat the food.
Well, so I don't know if it's the microwaves, but any instructions for cooking that you use. And honestly, most cooking involves boiling water. Even if you're not cooking something in boiling water, like if you're sautéing things, it's the act of like transferring the heat to your vegetables, and then the water inside your vegetables is heating to a certain temperature, boiling, because there's water inside. And you have to cook for a certain amount of time at this high temperature to cook the thing. Well, if your water now is boiling at a lower temperature, then you need longer times to cook, because just heating it to boiling is only heating it to 95 degrees, and you need a little bit longer time at that temperature to fully cook it. So cooking instructions often tell you to cook longer when you're at high elevations, and it's because of the boiling temperature. So yeah, it's pretty interesting stuff. So the millimeters of mercury is a very common unit we're going to be using for pressure. There are other pressure units. Torr, which is short for the guy who we named it after, Torricelli. Torr is actually the same scale as millimeters of mercury. So 760 millimeters of mercury is the same as 760 torr. But we also use something called atmospheres. And atmospheres is human readable because 1 atmosphere is what we think of as standard atmospheric pressure for us. So 1 atmosphere is 760 millimeters of mercury. Yeah?
So when you think about water evaporating, that's obviously not at 100 degrees C is the average temperature. But when it does evaporate in normal standard pressure, that means that it has to be above 100 degrees Celsius, that just one single molecule to escape.
So, this is the problem. Temperature is not an energy amount. So temperature it's complicated, but very complicated what temperature is. If you ask any physicist, they will be like, this is what temperature is, and it makes no sense. The way that in this class we're going to understand temperature is literally, it's a way to think about average kinetic energy, which is, and like I said, if you talk to a theorist, they'll be like, that's not what temperature is.
Yeah.
But for us, think of it as an average kinetic energy. Anything that is hot is going to have higher average kinetic energy. Anything that is cold is going to have lower. And the way temperature works is if you put something at high temperature next to something cold temperature, energy will transfer from the high temperature object to the low temperature object until they have approximately the same average kinetic energy. So they'll be the same temperature. That's what temperature is. It's not an energy. And so when you're talking about, okay, it's not that each individual molecule is at 100 degrees C. It's that each molecule has individually a large amount of kinetic energy. But that is balanced out by another molecule having a small amount of kinetic energy, and there's a lot of them, and they average out to an average kinetic energy, and that's what the temperature defines.
Yeah.
So you can't really define a temperature for a single molecule. That kind of makes sense, right?
Yeah.
Okay.
Actually.
Okay. All right. Besides these units, we're going to look into more, but the SI unit for pressure is the Pascal, which nobody uses because it's really not very friendly. But and then there is bar if you're a diver, and then there's PSI if you like car stuff, tires. There's tons of pressures. So we'll get to more pressure stuff when we do the gas chapter, okay? So right now we'll just stick with just this basic understanding. So again, when a liquid's vapor pressure suddenly equals the atmospheric pressure, whatever the outside pressure is, you get boiling. And that's what boiling is. It's suddenly that pressure reaches the external pressure. And hopefully it makes sense a little bit, because when you have evaporation occurring, you get some water molecules. So let's say it's an open container. Some of those water molecules are going to escape. And, for a brief period of time, they're going to be near the surface of the water. They'll eventually escape. And then, your water will generate more gas particles, and those will escape. But it's not boiling. It's just evaporating. But let's say that you're at the boiling temperature. Well, what's happening is you're generating the vapor pressure of your liquid has to be 760 millimeters of mercury. That means you've got to have a lot of molecules, of gas molecules of water, if you're boiling water, above the surface. But if it's open, they're constantly escaping. And so it's going to constantly generate more gas particles to replace the ones that are leaving. And that's why boiling is so violent. I mean, it's also hot, but that's why it's so violent. If you were to try to boil water in a closed container, it'll boil for a little bit, and then suddenly you'll make the 760 millimeters of mercury of gaseous water, and it'll stop boiling because it's reached the max. I think, yeah, it should do that. So it'll stop boiling once it's reached that pressure.
We had like a pressure cooker. Those will explode.
So pressure cookers, yeah, that's how you cook at a high temperature. Because again, most things, even when you're not like physically boiling water, most things cook because you're heating the internal water to boiling. So if you want to cook faster, you need a higher temperature, because water maxes out at 100 degrees, and that's when it starts to boil. And it kind of freezes it at that temperature until all the water's gone. So if you want to cook at a higher temperature, you need a pressure cooker. And that way you're creating this artificial environment of high pressure. And so now when you heat up your water, it is not going to boil at 100. It's going to boil at a much higher temperature now. And so you're cooking things faster because now you're cooking at a higher temperature. So like even a flame is higher temperature than water, than 100 degrees C. But like I said, most things we eat internally have water in them, and they will just cook at that temperature. That's it until the water's gone. Yeah. The food chemistry is odd. It's weird, but it's cool. I don't know enough about it. I wish I did.
So it increases the boiling point.
It increases the boiling point. That's what a pressure cooker does. Yeah. Yeah. So here are some actual numbers. So here's the Denver example. These pressures are now in atmospheres rather than millimeters of mercury. So 1 atmosphere is standard. So, if your elevation is 0 or 20 feet, which is hardly anything, water is going to boil at 100. In Denver, water is going to boil at 94 degrees. On Mount Whitney, it's going to boil at 87. On Mount McKinley in Alaska, it's going to boil at 83. And at the top of Mount Everest, the highest mountain in the world, it's going to boil at 78 degrees. I mean, you're going to need a gas mask because the pressure is about a third of what you're used to. But, Huh?
At least you can boil your eggs easier.
No. It takes longer to cook in them.
Oh, wait.
So the water boils, but it's cooking at a lower temperature, so it takes a lot longer for the eggs to cook. So you got to denature the protein, you're close to space when you're on Mount Everest. Closer to space, I should say, not that close. All right. So since we've been talking about liquid going into gas, let's kind of focus a little bit on phase changes in general. I think some of these are fairly easy to understand, melting and freezing. I believe you mostly understand vaporization, liquid to gas, and condensation, gas back to liquid. Maybe these are new, maybe not. Solid to a gas is sublimation. That's what dry ice does when you put it in water. It just turns directly into a gas. It doesn't go through the liquid phase. This happens with ice cubes in your freezer. I think I talked about this. You leave your ice cubes in a tray for a month or more, they will visibly shrink. And that's because that solid ice is turning into a gas. It's sublimating. And then if you've got a not great freezer, that gaseous water will eventually redeposit back onto ice, and you'll make all these ice crystals surrounding your little frost freezer. That's deposition. We use that word a lot. So like chemical vapor deposition, I think I showed you guys the diamond growing video. That's deposition. You turn gas atoms into solid carbon in diamond. So some new terms. So we're going to understand which of these are endothermic or exothermic. And if you're not familiar with those terms, endothermic means that energy has been absorbed by whatever is absorbing it. Exothermic means energy has been released. Okay. We also want to understand how much heat is required. So what are the relative amounts of heat? Which requires more heat? Vaporization or melting? Things like that. So these heat amounts that we're going to talk about, like how much energy is required to do these phase changes, we're going to refer them by the word enthalpy. We're going to talk about enthalpy. Let's put it this way. And enthalpy is just a form of energy. And it's not going to be very satisfying, but there is a good definition for you. It is the heat content of a substance at constant pressure. And you don't need to know this, but just in case you are mathematically minded, enthalpy, which is H, is equal to internal energy plus the pressure times the volume. This makes no sense to everybody. I will agree. It doesn't make any sense to me. But that is the definition of enthalpy. So this is why enthalpy is a little bit tough to start out explaining. But what I'll say is this. The reason that chemists use enthalpy a lot is because it's a very convenient value to measure. It's very easy to measure enthalpies. And that's because the easiest time to measure an enthalpy is when you're doing a change, any kind of process under constant pressure. And if you think about anything we've done in any lab experiment, it's all been done at a constant pressure. How you mix two solutions together, what is the pressure? It's the atmospheric pressure. That's not changing. Anytime I do any kind of experiment, most of the time the external pressure is going to be the same. We're doing it under open atmospheric conditions. We're not doing it in a closed container. Yes, we can do experiments in closed containers. We can generate bombs if we want, but that's a different scenario. That's changing pressure, and that makes the enthalpy a lot harder to measure. But honestly, enthalpy is a very convenient thermodynamic property. This is the beginning of thermodynamics. And again, if you're more interested in exactly what it is, you'll have to take a higher level class because it's kind of crazy. I guess the best I can tell you is enthalpy, the way to think of it is the amount of energy a substance has plus, and this PV term is a little bit weird, the amount of pressure and volume you need to move the universe out of the way to make room for that stuff. That's kind of what that PV term is for. It's a weird idea, so that's why I'm not a fan of it, but that's the best I can tell you at this point. Just think of this as a way to describe energy changes that makes things easy for every calculation. Yes?
Just wondering, like, what the internal energy, or like how that's defined, temperature, or?
No, it's like all of the. I would like to say it's the potential energy and the kinetic energy, I think, all together. I think. I could be saying that wrong. But internal energy is another one that's. Yeah, I think it's all of that together. Is it? I'll have to go back and think. I haven't. All right. I'll have to think about that. I'll come back to it. Okay. So enthalpy. We're just going to use that as a substitution for energy. As we've been talking about energy for anything, we're just going to use the word enthalpy. And, you know, the absolute enthalpy, how much energy does this thing have? That's not what's interesting. Although it is interesting, but it's not something that's easily measured. What's more easily measured is how has the enthalpy changed. So we're going to be focusing on changes in enthalpy, and that's where this delta comes in. Delta H is a change in an enthalpy. And when you look at phase changes, so here we've got the state of a solid. It's at a certain enthalpy, whatever that is. And when I melt that substance, it requires this much energy change, this change in enthalpy. And so now it's a liquid, it's at a higher overall energy, right? Because liquids have more energy, they have more kinetic energy. If I want to turn my substance into a gas, it requires this change in enthalpy. And so that's the vaporization. Notice that the melting and the vaporization, if I add those two energies together, that is equivalent to the energy required, or the enthalpy required to go directly from solid to gas. So there's no extra energy to go solid to gas. There's no shortcut. It's the exact same energy as going in steps from solid to liquid to gas, or going straight from solid to gas, same enthalpy. And the reverse is exactly the same as well. When I go back from gas to solid, the change in enthalpy, the amount is the same, but the sign is the opposite. So these enthalpy changes are all positive because you're adding energy to the system. These enthalpy changes are all negative because you're taking away energy. These are endothermic changes because you're adding energy to the system. These are exothermic changes because you're taking away energy. So notice that even though this is deposition, we're using the same values for sublimation. We're just putting a negative in front of it. That's it. The enthalpy change for sublimation is exactly the same, but the opposite as the enthalpy for deposition. Same value, just opposite sign. Now, if you are keen-eyed, you might have seen that makes sense, vaporization. That makes sense, sublimation. What the hell is FUS? So for melting, we have a different term for the enthalpy change. And it doesn't make sense, but it's enthalpy of fusion. It sounds like it should be the opposite, because melting is solid to liquid. but enthalpy of fusion is solid to liquid, even though it sounds like it should be liquid to solid. But it's solid to liquid. It's the enthalpy for melting. Don't ask me why, I don't know. I've never looked it up. I just accept it. And then we have different names for these as well. So let me get to that. Okay. So here is just the liquid to gas transition. So these are expected. Delta H for vaporization is the same value as the delta H for condensation. They just opposite sign. There's the negative. This is an endothermic process. This is an exothermic process. Vaporization is always going to be a positive value, always, because you're adding energy. It's endothermic. Okay. For the next one, here are some new names. So like I said, heat of fusion. By the way, another term that we kind of throw around without explaining is enthalpy of fusion versus heat of fusion. They mean the same thing. So when you say enthalpy of fusion or heat of fusion, that means the same thing. So heat and enthalpy in these contexts mean the same thing. Okay. So here's another one. Liquid to solid we think of as freezing, but we call the enthalpy by a different term as well. So it's enthalpy of, or heat of crystallization. Anyway, but these are opposites as well, okay? Okay. So here's where we're going to switch gears. We're going to talk about, well, we're going to go to this page, although not this page. I think it's page 88. It doesn't have a chem activity number. It's just a random chem activity assignment in the middle. I think it comes after 24B or maybe 24C. But I think it's page 88 in your book. And here, let me fix that. Well, I can't fix it. So go to page 88, do questions 1 through 8. It's just kind of reinforce these ideas of enthalpy, hopefully, in your head. We can talk about the answers. And after this, we're going to do... Oh, you don't have an 88 at all? Oh, it's stuck in the homework. Okay. Yours, yeah. It's okay. You can turn it in again after, it's fine. And I was going to say, after this, we're going to do like the bane of 222 students, which is the Clausius-Klaproth equation. But we'll get to that. You'll see. It's not that bad, but people stare at it like, what the hell is that?
Yeah.
Is it there? I know. 88. Yeah. Huh.
I think you're trying
I think you got it.
Yeah, and then water for.
Oh, this is like 4.5. This is like way ahead of time. I think maybe you already turned it in, but also from another problem set.
Wait, didn't you?
Though I don't think I would have. Yeah, you did the homework that's like next week, or not even that, but yeah.
Oh, no, ethanol, not ethanol.
I don't have the other stuff with me. Do you mind working with somebody? Yeah.
Is H vaporization liquid positive or negative? Vaporization positive? No. Yeah.
Yeah, for vaporization.
Yeah.
Oh,
That's becoming from liquid to solid, or liquid to gas, or.
Yeah, so it's positive.
For some reason you have the right page number. You have an older version probably. No, that's it.
Okay.
You have the old one, which is fine. Yours matches up.
Did you buy that at the bookstore?
They had old copies, I guess, of the
It's fun.
year ago one.
So underacid is the absolute
They're probably.
No. For these three. So if you're looking at, the heat of vaporization for these three, which one And so they say absolute value because they don't want to give away positive or negative.
Yeah,
So
okay.
ignoring the sign, which is the smallest one.
Okay. Wait, it just
Close to 0.
yeah, that's right. Is this right?
So it's the value.
Just to be clear.
Yes. Correct. Yeah, yeah.
Fine, I'll make it smaller.
Yeah, this is just, making sure everybody's on track.
Yeah.
Yeah.
Organizing the thoughts.
And then the largest one.
You guys want
Yeah. Or mental function.
Wow.
Why have I shrine to James Cameron in my room? Someone of mine, so. Okay, sketchy.
What he's not telling you is it's all titanium.
It's the first movie I ever went to. Did your energy diagram, did you just do
Did we see
the thing?
this? Was that what, this little?
Yeah, sort of, yeah.
Yeah.
So you can just do levels and just say, well, if they are all starting here, to go from the liquid to the gas, how much of a jump would I need? Or how much change in energy would I need?
Okay.
Oh,
That's
wait,
more,
so
that's
it's just
like the,
is that like this?
the vapor pressure
over
one,
the-
a little bit.
Yeah, is that what he's asking?
No, not this one. So exactly like the one we saw, this one.
Okay.
It's just you're going to have different points for each of your liquids.
Okay.
So this is just one
There's so many charts
specific
that we have to
liquid.
remember.
Yeah.
Oh, next one's about the.
We can do that in the board together too. So if it doesn't make sense.
I didn't even draw it. I was obviously waiting for you to figure it out.
I think like this, if that's the graph.
So your energy diagram, like the one where we saw solid, liquid, gas, those arrows going up and down. That's kind of what we're looking at for.
But yeah, the next one was also one. I was eventually.
Okay.
I think this is the good one. For me, it's been on this page.
Should we start to talk about the answers, or you still want to go through it? It starts getting hard when you do the Wolfsman one, that's for sure. Yeah. Hey, who just walked out? Oh, it's okay, Max. Okay, let's talk about the answers. So for the first few questions, it's looking at water, methanol, hexane, and the liquid which requires the least energy per mole to vaporize is hexane. Yeah, it's got the weakest IMFs, just London dispersion forces. That's it. And the most? Water, thank you, because it's got two sides that does hydrogen bonding versus methanol only one. So the delta H of vaporization for these liquids is positive. It's always positive. Vaporization is liquid to gas. You have to add energy to make that happen. So positive. It's an endothermic process. And then for which liquid is the absolute value of delta H the smallest? Somebody said hexane. It is hexane. So hexane's got the weakest IMFs. You don't need much energy to break those IMFs to turn the liquid to a gas. So that's hexane. and then the largest is going to be water because it's got the strongest IMFs. So when you're talking about drawing an energy diagram, this is all relative. Or enthalpy diagram, not energy. But let's say that they all start here. Whatever that energy is, this is the liquid for all of those substances. Well, hexane doesn't need much enthalpy to turn into a gas. So to go from liquid to gas for hexane just takes this much. For methanol, it's going to take more energy. Methanol, I can't spell today. So there's the amount of enthalpy required to go from liquid to gaseous methanol. And then for water, gas water, which is steam, goes, gas water, there we go, goes from there to there. Water as a gas. So that's kind of the generic energy diagram. That's the kind of diagram we're going to be drawing for an energy diagram for thermodynamics. So we'll focus on this when we get to the thermodynamics section a little bit more, but when we talk about thermodynamics, we're going to be talking about state. Like, hey, liquid is at this energy state, gas is at this energy state, and how do you go from there to there? That's kind of the basic idea behind all of these changes we're going to think about. So now 6. This is a tough one. So sketch a Boltzmann distribution curve for each substance. They are all initially at the same temperature. So notice that this has got kinetic energy on the x-axis. Y-axis is particles. And all you got to do is look at this. Kinetic energy is proportional to temperature and nothing else. So if they're all at the same temperature, they will all have exactly the same Boltzmann distribution. It doesn't matter what they are made of, doesn't matter what the IMFs are, the Boltzmann distribution is going to be the same. So it's going to be a generic looking curve, looks like this. It's going to peak and then taper off like that. They're all going to look like that. What's going to be different is where that threshold energy is for whether they can turn into a gas or not. That's what's going to be different. But the distribution of kinetic energy for the molecules in that liquid, they're all going to look like this. Because if they're at the same temperature, then they have the same distribution of kinetic energies. Now, what's going to be different is if this is not kinetic energy. If this was velocity, then we're going to look at the mass, and that's going to play a role, because the heavier something is, the slower it's going to move. The lighter something is, the faster it's going to move. All right, but if it's just kinetic energy down here, they have the same distribution. And so I can just draw the same curve 3 times, overlapping, and they all have the same, label them all the same. Okay, so now we've got this graph here that shows delta H of fusion, which is the melting enthalpy, and delta H of vaporization, which is liquid to gas. In all cases, liquid to gas is a lot more energy than solid to liquid. Why? Anybody know? Why is it so much, take more energy to go from liquid to gas than solid to liquid?
Gas already has more energy.
Well, if it already has, well, gases definitely have more energy. But why do they? IMFs, what about them?
They're stronger in the liquid form. So it takes more energy to release them into gas.
You're super close. So think about it this way. Whether they're in solid or liquid, the molecules are fairly close together, and the distance will affect the IMFs. But when you're melting something, are you completely breaking the IMFs? No, all you're doing is weakening them to the point where now the molecules can move around each other. But they're still close together. So you're not completely breaking the IMFs when you go from solid to liquid. You're just weakening, the attraction such that they can now move around. Liquid to gas, though, you are completely breaking the intermolecular force attraction between 2 molecules. So it takes a whole lot more energy to completely separate those molecules from each other. So that's why the delta H of vaporization is so much higher than a delta H of fusion. Okay. So you were very close. All right. So next, we're kind of bouncing around topics a little bit here. So we're done talking about phase changes, and we have a kind of a framework for talking about them, and we can talk about their energy amounts. So next we're going to look at this thing. So this is the Clausius-Clapeyron equation, this thing right here. And what it does is it describes these curves, which you've seen already. These are the vapor pressure curves. Vapor pressure versus temperature. So notice that they are all shaped like this. They're exponential. As you increase the temperature, the vapor pressure exponentially increases. And the reason is because this is the equation. This EXP, by the way, is another way of writing the E thing. So you know, the reverse of the natural log, Euler's number, that 2.7 something number. That's this E. That's that EXP thing. So this is really written as the vapor pressure is equal to beta times e to the power of delta H vaporization over RT. That's really how, I mean, that's just the typed way to write it, but this is the way it really should be written as a mathematical equation. So this is how you describe the vapor pressure versus temperature curve. Now, a couple things. So we know what delta H vaporization is. This is the enthalpy required to vaporize something. And it makes sense that's in here because that's involved, right? This is going to describe how much energy is required to break the IMFs to go from a liquid to a gas. That's going to affect your vapor pressure. We've got these other things, though. R. R is the gas constant. It's like one of the most important constants we're going to come across in chemistry. It's everywhere. Oh, so far it hasn't been anywhere, but now we're going to see it everywhere. And it's got a bunch of different values. It depends on what units you need. So we're going to see it. Is that mine?
No.
It's yours. Okay. So, oh, it's the sticky keys. Yeah. So we're going to see a value for it soon. In a second, it'll pop up when I hit the next button. But our value, since we're dealing with energies, right? This is delta H is measured in energy values, joules and stuff. And we have temperature here. So we're going to use a version of the gas constant that has joules in it and temperature in it. There are other versions of the gas constant that have pressure and volume and stuff, liters and atmospheres, things like that. So be careful of which gas constant you use. Beta is another constant that we're not going to care too much about. It shows up in this equation. It's something we can calculate. It doesn't have a whole lot of meaning to us at this point. So we're not going to talk about it too much other than understand how to calculate it if you want. So, and it depends on the gas. So it does change. R is constant no matter what kind of gas, okay? Beta does depend on which particular gas you're using.
Will beta be given, or you're saying that's something we'll have to find?
And I'll show you, yeah. So this version of the equation is not super useful to us. It does explain why the curves are shaped like this, but this is not the version we're going to be using. We're going to be using another version. Notice that this equation has been rewritten into the form of a straight line. So a straight line on a graph has a form y is equal to mx plus b. M is slope, b is your y-intercept. And the way that you can break this apart is your y is now going to be natural log of vapor pressure. Your x is going to be 1 over the temperature, inverse temperature. And your slope is this thing, negative delta H of vaporization over R. And your b is natural log of beta. So I will show you how we derived it just in case. This is not something I'm going to ask you on an exam, but in case you're curious, we do need to understand a little bit of algebra. You need to know how logs work. So let me make sure that that's clear. So if you start with this form, what I will do first is take the natural log of both sides. Okay? So natural log of here, natural log of this whole thing. And one of the properties of a log is you can split the contents of a log. So if you've got something times something inside of a log, that separates out as the log of b plus the log of that other thing that you're multiplying. This is a property of logs. So you may have forgotten how to do an algebra. But, so that's that. Now the other property of a log is the natural log of e. When you have that scenario, the e to the power, this power will come out and become a constant in front of this thing. So this becomes natural log of beta plus, let me take away the plus because now there's a minus delta H vaporization over RT. And natural log of e to the 0, or e to the 1 is 1. So this goes away. And you're left with that. So that's how this works. And if you do some rearrangement, you can swap these sides. And I can separate the T out, and I can make it so delta H vaporization over R 1 over T, like that. It's still the same, plus natural log of B. And now I've got my Y part. I've got my slope. And I've got my X value. And I've got my Y-intercept value. So that's the form of the Clausius-Clapeyron equation we're going to use. And so what is this good for? Let's say I take some methanol and I go to the lab and I keep it at 20 degrees C and I measure the vapor pressure. So I have a data point. At 20 degrees C, the methanol vapor pressure is whatever it is, this pressure. And then I heat the methanol up, 30 degrees. I measure the vapor pressure. 40 degrees, measure the new vapor pressure. I'm going to have a series of temperature versus vapor pressure points. That's kind of, I'm varying this and I'm measuring this. But I'm not going to plot temperature versus vapor pressure, because if I do, I'll get those curves. If I plot instead natural log of vapor pressure versus 1 over the temperature, I will get that, a straight line. And I can use the slope and the y-intercept to then calculate delta H of vaporization. And if I need the constant beta, I can get beta as well. So just really quickly, this thing, if you notice, on the x-axis we have 1 over the temperature. So if I think about which way is temperature increasing, temperature is actually increasing that way. Because 1 over 10 is a tenth, 1 over 20 is a smaller number. So going smaller for inverse temperature means you have a larger temperature. So it's increasing to the left. But what are we going to do with this? So again, we're going to use the slope and the y-intercept. So a computer gave me this straight fit line. The computer calculated the slope for it. It calculated the y-intercept. So if I extend this to 0, wherever the 0 is here, and I find where this thing crosses the y-intercept, it crosses it at 18, so pretty far. I can't see it on this thing, but it does cross it at 18. And the slope is this number. It's a negative slope, makes sense. It's going downwards like this. So first thing first, sometimes we're going to ask you to write down the results in the Clausius-Clapeyron form. This is what a computer spits out. The computer has no idea what x and y are, but you do. You know that y is natural log of the vapor pressure. You know that x is 1 over the temperature. You know that the units for the slope are going to be Kelvin, and the units for the y-intercept are going to be unitless. So let's talk about that for a second. So going up to here. So this is the equation that we're plotting. I'm not going to get into the y, but whenever you take the log or the natural log of anything that has units, the units formally disappear. And technically the reason why is because, and we're not doing this consciously, but technically is when you take a log of something, you have to divide it by the standard value. So something with, so I would basically be taking vapor pressure and dividing it by a standard value that has the same units, and so the units would cancel that way. But you don't have to do that. All you have to do is remember that when you take the natural log of something, the units disappear. So this is unitless, that is unitless. That means this whole term needs to be unitless. So you know temperature has Kelvin units. So this Kelvin in the denominator has to cancel out with kelvins here. And that's why the slope has units in Kelvin. Okay? So everything has to be unitless in the end. And so that's why your slope has units of Kelvin. They cancel out with the 1 over Kelvin. Okay. So that's the first thing. Then we can kind of figure out what delta H is. So again, the slope is negative delta H over R. Right? That's what slope is. That's what we define slope as. So I've got my slope. It's negative 2,993.8. R, here's our first look at what R is. R is 8.314 joules per mole per Kelvin. We'll give this to you, don't worry. So you plug in R, you plug in your slope. So again, slope is negative delta H over R. You plug in slope, you plug in R, you solve for delta H of vaporization. Now, this thing is taking a shortcut. This thing is converting R from joules to kilojoules automatically. You don't have to do that. You can do it afterwards. But in general, your enthalpy values normally are given in kilojoules per mole. So if you have a value that ends up in joules, convert it to kilojoules to make it easier to read. Otherwise, it's going to be a really big number, 24,900, something like that. So it's a lot easier to read in kilojoules. So there we go. We calculated the delta H of vaporization. Make sure the sign makes sense. It has to be positive. It's a delta H of vaporization. So if you get a negative value, you did something wrong. And they're going to be about that big. So if you get something wildly huge or tiny, did something wrong. Okay, so that's how you get delta H. You might also want to calculate beta. So how do I get beta? Well, the y-intercept is equal to the natural log of beta. I've got a y-intercept. There it is, 18.01. So plug in 18.01, solve for beta. So how do you do the reverse of a log? You take e to the both sides. The result of that natural log comes out, and it becomes beta. E to the natural log of 1 is 1. That goes away. And so if you do e to the 18.01, you get this giant number. There you go. And I believe it's unitless as well. Let me make sure. Yeah, it should be. It actually doesn't matter. It's going to be a little bit complicated to talk about what it could be. But just treat it as unitless for now. Okay. So you can calculate 2 of these values from these graphs, okay? So let's try this ourselves on the board slowly to make sure we understand how this works. We're going to probably look at a third form of the Clausius-Clapeyron equation on Thursday. But for now, let's just do this. And so, again, start off with rewriting what the computer spits out at you into a Clausius-Clapeyron equation. So I've got my log of vapor pressure is equal to my slope, negative 7,377. And that's going to be in Kelvin units, times my whatever temperature, plus my beta value, or the natural log of beta, so my y-intercept, 18.47. So that's the equation we're kind of looking for to start with. And now let's solve for delta H of vaporization. So we know that the slope of this line is equal to negative delta H vaporization over R. So the slope is negative 7.377. R is going to be 8.31 joules per Kelvin per mole. And if you rearrange things and solve for delta H of vaporization, you will get, it's not too hard, so once you get over the nasty looking equation, I think the math isn't too bad, right? So I move this up here, we're going to multiply them together. Negative 7.377 times 8.31. That negative gets moved over here, so the negatives cancel. I end up with 61,302 with sig figs. Joules per mole, the kelvins cancel. We don't normally see joules. That's a big number, so let's convert it to kilojoules. I divide by 1,000, and it becomes 61.3 kilojoules per mole. So there's your delta H of vaporization. That one's a lot bigger. This one has much stronger IMFs than the last one did. Well, that makes sense. It's mercury. Mercury has got really strong metallic bonding that holds the atoms together. That's pretty strong. So you're going to have a really high vapor pressure. Delta H of vaporization. Last but not least, let's get the beta. So natural log of beta is equal to the y-intercept, 18.47. So I will do e to the both sides of this. So e to the natural log of beta, e to the 18.47. This beta comes out. You get beta is equal to e to the 18.47, which is, and it's almost always the button above natural log on your calculator. It's not the EE times 10 to the power thing. It's a different one. 18.47. That's Euler's number, I believe. So really large number, 1.05 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8. So there's my beta. That's it. So it looks nasty, but it's not hard to do, like once you understand what we're looking at. And again, where did this data come from? This came from somebody did an experiment where they measured the vapor pressure of mercury at different temperatures. And they got this vapor pressure curve. But instead of plotting it pressure versus temperature directly and got that curve, they plotted 1 over the temperature versus natural log of pressure. And that gives you a straight line fit, which you can find the slope of, and you can plug into this equation and find delta H for. Okay? So we'll actually, I think we'll do the whole thing at some point. We'll actually get the raw data, we'll plot it from scratch, we'll find the delta H from scratch, basically. Okay? But that is the Clausius-Clapeyron equation.
What a name.
Yeah. Yeah. All right, so let's stop there. I don't want to go any further than this. There is I'll mention the third form of the Clausius-Clapeyron equation is a form, I'm not going to do it now, is a form that combines 2 of these together. And basically it lets you plug in one pair, a pressure and temperature, and then solve for another pressure or temperature. And that, we'll see how that becomes useful later. So we're going to add to our concepts with that. So yeah.
Well, I have a question about Thursday's quiz.
Oh yeah, okay, quiz. So last week we covered basically IMFs and everything to do with intermolecular forces. So what affects intermolecular forces? So it's going to be functional groups. So I'm identifying, hey, where's the functional group? What kind of functional group does this compound with this name have? So understanding the ending is the OL means it's got an alcohol. Comparing different compounds. This one is a longer chain, so it's going to have stronger IMFs. It's going to have more London dispersion forces. This one has this shape. It's more long than round, so it's going to have stronger IMFs. This one has more steric hindrance. So this, it's got more blocking to the functional group. This one has more accessibility to the functional group, so it's going to have stronger IMFs. So it's going to be a lot of comparing molecules to understand what's got the stronger IMFs and what does that mean for boiling point. So we talked about stronger IMFs means higher boiling point. Stronger IMFs means higher viscosity, higher surface tension. We won't do anything from this week, though. Okay.
So lectures 7 to 9
Y-
because we did lecture 10 today.
yes, 7 through 9. Yes. That makes sense. Thank you.
As far as the actual.
Yeah, I guess it would be connectivity 25, 25A. And I'm trying to think if 25B is on there. Probably. Yeah, I guess 25B as well. Although that's mostly just, 25B as well. So 25, 25A, 25B. Is that, which one had the functional groups? Is that 25? I think so.
Whatever we did on the third.
Yeah. 25 had the functional groups, yeah. Okay.